We went to the moon. We landed human beings on the surface of another world, brought them home safe, and we did it 6 times. So going to Mars, that's just the next step, right? Same basic idea, just a little farther away, a little more fuel, a little longer trip, a little more food and water, but fundamentally the same problem. I mean, we did the hard part already. We cracked the nut. Mars is just further down the same road. That's completely wrong, and I'm going to show you exactly why. See, this is one of those situations where common sense leads you straight off a cliff because the moon and Mars are not the same problem at different scales. They are fundamentally different problems, and the difference is not the kind of thing you fix by building a slightly bigger rocket or by packing a few more sandwiches. The difference is mathematical. It lives inside an equation, a very simple-looking equation, and that equation is merciless. Let me take you through it. And by the time we're done, you are going to understand something that took engineers decades to fully reckon with. Getting to Mars is hard. Landing on Mars is really hard. But getting off Mars and coming home, that is a different kind of hard. That is the kind of hard where nature says no, and you have to figure out whether it really means it. First, let's make sure we agree on what a rocket actually does, because if you don't understand this, none of the rest makes any sense. A rocket works by throwing stuff out the back. That's it. That is the whole secret. You throw mass in one direction, and by Newton's third law, the rocket goes in the other direction. Every rocket that has ever flown works on this one idea. You burn fuel, you heat it up, you blast it out a nozzle at tremendous speed, and the rocket moves the other way. Simple. But there is a catch, and it is a devastating catch. The fuel you are going to burn later, you have to carry it now. And carrying it now means your rocket is heavier now, which means you need more fuel to accelerate all that fuel, which means the rocket is heavier still, which means you need even more fuel to carry that fuel too. You see where this goes? It's a spiral, a vicious, unforgiving spiral. There's an equation that captures this spiral perfectly. It was first worked out by a Russian school teacher named Konstantin Chilovsky back in 1903, the same year the Wright brothers flew at Kitty Hawk, and here it is in plain words. The change in velocity you can achieve. Your delta V equals the exhaust velocity of your engine times the natural logarithm of the ratio of your full mass to your empty mass. That's it. Delta V equals exhaust velocity times the log of the mass ratio. Now, if you've never tangled with logarithms and exponentials, let me explain what this means in practical terms, because this is where people get tripped up. They think, well, if I need twice the speed, I need twice the fuel. Wrong. You need much, much more than twice the fuel. The relationship is exponential. If you flip the equation around and ask how much fuel do I need for a given speed, the answer involves an exponential function. And exponential functions are not kind. Let me give you a feel for it. Suppose your engine throws exhaust out at 3 km/s. That's a decent chemical rocket. If you need a delta V of 3 km, you need a mass ratio of about 2.7, meaning your rocket at launch has to weigh about 2.7 times what it weighs when the fuel is gone. Okay, that's a lot of fuel, but it's manageable. Now suppose you need 6 km/s. You might think, well, twice the speed, maybe 5 times the fuel. No, the mass ratio jumps to about 7.4. How about 9 km? Says 3 times the original. The mass ratio is about 20. Your rocket is now 95% fuel by mass, and at 12 km west, the mass ratio is about 55. At that point, you are basically trying to fly a thin metal can wrapped around a lake of kerosene. There is almost no room left for the actual payload, the stuff you're trying to deliver. This is what engineers call the tyranny of the rocket equation, and it is not an exaggeration to call it tyranny. It dominates everything about space travel. Every rocket that has ever been built has been shaped, twisted, and constrained by this one equation. Let me give you an analogy so you can really feel this in your bones. Imagine you're going on a road trip across a desert, but there are no gas stations anywhere along the route. You have to carry all your gasoline with you. Fine, but gasoline is heavy, and carrying that extra weight means your engine works harder, which burns more gasoline. So you need extra gasoline to haul the extra gasoline, and that extra gasoline is also heavy, so you need more gasoline on top of that. Each new gallon you add gives you a bit more range, but it also makes the car heavier, which eats into the range you just gained. Eventually, you reach a point where adding another gallon barely helps at all because the fuel is mostly being used to carry itself. That's the dilemma rockets face. And it's actually worse than my desert analogy because a car on the ground just fights friction and gravity going uphill. A rocket has to throw mass overboard at tremendous speed just to accelerate forward. Every second it flies, it's getting lighter, which is good, but it started absurdly heavy, which is the whole problem. The Saturn V, that magnificent machine that took us to the moon, was about 85% fuel by mass at launch. Think about what that means. It weighed about 12 million pounds sitting on the pad, 6.5 million, and the part that actually went to the moon and came home. The tiny command module with 3 men inside weighed less than 1% of the total. All the rest was fuel and the tanks and engines to burn that fuel, and those were thrown away along the route stage by stage to shed dead weight. The entire design philosophy of the Saturn V was about getting rid of mass as fast as possible. Use it, dump it, move on lighter. That is not elegance. That is desperation dressed up as engineering brilliance. The equation forced that design, not the engineer's preferences, the equation. Now let's talk about the moon trip and let's see why it worked. The delta V to get from the surface of the Earth into low Earth orbit is about 9.5 kilometer ascess. That's the hardest part of any space mission. Getting off the ground, you're fighting gravity the whole way. You're punching through the atmosphere and you need tremendous speed, about 9-12 kilometers s of it. From low Earth orbit to the moon and back, the additional delta V is roughly another 6 kilometers, says total round trip, and there are some clever tricks. The lunar module was very light. It only had to work in the moon's weak gravity, 1/16 of Earth's. The moon has no atmosphere, so no heat shields needed for landing, and the moon's escape velocity is only about 2.4 kilon, so getting off the surface didn't take that much fuel. They left the bottom half of the lunar module behind. They ascended in just the top part, this little cabin, barely enough for 2 men. They rendezvoused with the command module in orbit, transferred the crew, and threw the ascent stage away too. Every kilogram mattered. Every decision was about saving mass, and it worked. Barely in some cases, but it worked. The total delta V budget for the whole Apollo mission from Earth's surface to the moon's surface and back was roughly 15 to 16 kilometres. That's a monstrous number. The Saturn V was the most powerful rocket ever flown, and it could just barely do it. So now Mars, the first thing you have to understand is how far away Mars actually is, not in some abstract sense. In a practical mission planning sense, the moon is about 3 days away. You light your engine, coast for 3 days, and you're there. If something goes wrong, you can turn around. Apollo 13 proved that. They swung around the moon and came home in a few days, battered but alive. Mars is not 3 days away. Mars at its closest is about 55 million kilometers from Earth. At its farthest, about 400 million kilometers. And you can't just point your rocket at Mars and go, because Mars is moving. Earth is moving. Everything is orbiting the sun at different speeds and different distances. You have to launch at just the right time, follow a curved path called a home-on-transfer orbit, and arrive at Mars about 8 or 9 months later. 8 or 9 months in a spacecraft in deep space with no possibility of turning around because you're already committed to the trajectory. Let me make sure that sinks in. 8 or 9 months on the space station. If something goes terribly wrong, you can pile into a Soyuz capsule and be on the ground in a few hours. On the way to Mars, if something goes wrong, you are in a metal tube, hurtling through the void at tens of thousands of kilometers per hour, and your options are to fix it yourself or die. There is no abort. There is no safe harbor between here and there. The vast majority of the journey is spent in a region of space where the sun's radiation is unfiltered. Micrometeorites are an ever-present threat, and the nearest human being, not on your spacecraft, is getting farther away every day. And people talk casually about this trip as though it's a long airplane flight, as though boredom is the main concern. It's not. The main concern is that you're living inside a complex machine for the better part of a year. And if any critical system fails, engine, life support, navigation, power, there is no emergency landing strip between Earth and Mars. Nothing, just vacuum. But let's set aside the travel time for now. Let's talk about delta V, because that's what the rocket equation cares about. From low Earth orbit to delta V to get on a transfer orbit to Mars is about 3.6 kilometers. Then you need to slow down when you arrive. Maybe another 1 to 2 kilometer s to get into Mars orbit. Then you need to descend to the surface. And this is where Mars starts to show its teeth. Mars has an atmosphere. You might think that's good news. On Earth, we use the atmosphere to slow down. Parachutes, heat shields, air resistance, wonderful stuff. Saves you all the fuel you'd need for a powered landing. And the moon has no atmosphere at all, so everything there had to be done with rockets. But Mars has a terrible atmosphere. Not terrible in the sense that it's unpleasant, although it is terrible in the engineering sense. It's the worst of both worlds. The atmosphere of Mars is about 1%. The density of Earth's atmosphere at sea level, 1%. Standing on the surface of Mars is like standing at an altitude of about 35 kilometers above the Earth, about 3.5 times higher than commercial airplanes fly up, where there's essentially nothing. That's how thin the air is on Mars at ground level. So what does that mean? It means the atmosphere is thick enough that you cannot ignore it. When a spacecraft comes screaming in at 5 or 6 kilometers S, even that wisp of air generates enormous heating. You need a heat shield. You have to manage the thermal loads. It's a real atmospheric entry with real danger, but the atmosphere is far too thin to stop you. On Earth, a parachute can slow you from supersonic speeds to a gentle landing. On Mars, a parachute helps, but it can only slow you to about 200 men. Maybe a little more, maybe a little less, depending on the size of your parachute and the weight of your vehicle. And 200 mph is not a landing speed. That's a crashing speed. So after your heat shield has slowed you from hypersonic to supersonic, and your parachute has slowed you from supersonic to something still terrifyingly fast, you then have to fire rockets to do the final braking. For a small robotic lander, this is manageable. The Viking landers that touched down on Mars used a combination of heat shields, parachutes, and retro rockets, and they weighed under a metric ton. It worked. The engineering was beautiful, but those were small machines with no passengers. And the signal delay from Mars to Earth is over 10 minutes, sometimes over 20. That means no one on Earth can steer the landing in real time. The machine has to land itself, and every step of the sequence has to work autonomously. Any failure, and you've just made a very expensive crater. A human mission to Mars needs to land something like 20 to 40 metric tons on the surface. People, habitats, life support, food, equipment, power systems, and possibly the fuel and vehicle for the return trip. Here's where the nightmare truly begins. That parachute trick does not scale. You cannot just build a bigger parachute for a heavier payload and expect it to work. The physics doesn't cooperate. The atmosphere is so thin that the parachute would have to be absurdly large, hundreds of meters across. And deploying something like that at supersonic speeds in Martian atmosphere is, to put it gently, beyond what we currently know how to do. So for heavy payloads, you need to use rockets for most of the deceleration. And every kilogram of rocket fuel you bring for landing is a kilogram you had to carry from Earth. The tyranny of the rocket equation. Again, NASA has estimated that for an all-propulsive landing on Mars, every 1 metric ton you want on the surface requires about 20 metric tons in low Earth orbit. That ratio 20T-rho1 should give you nightmares if you're planning a Mars mission. But I keep getting ahead of myself. All of it is just the problem of getting to Mars. Let's suppose by some magnificent effort we solve it. Let's suppose we land a crew on Mars with their habitat and their supplies and their equipment. Let's suppose everything goes perfectly. Now they want to come home. And this is where the universe laughs at you, because getting off Mars is in many ways harder than getting to Mars. Not because Mars has stronger gravity than Earth. It doesn't. Mars has about 38% of Earth's surface gravity. The escape velocity from Mars is about 5 kilometers compared to 11.2 for Earth. So in raw gravitational terms, Mars is easier to leave than Earth. But you're not on Earth anymore, you are on Mars. And Mars has no Kennedy Space Center, no vehicle assembly building, no army of engineers, no factory down the road manufacturing rocket parts, no tanker trucks delivering fuel. You are on a barren, frozen, airless world, 55 million kilometers from the nearest machine shop. And you need to build or bring everything required to launch a rocket from the surface of another planet. Think about what it took to launch the Saturn V. Thousands of people, billions of dollars, entire industrial supply chains. Just the liquid oxygen and liquid hydrogen to fuel that rocket required enormous industrial infrastructure, cryogenic processing plants, pipelines, pumps, storage tanks. All of it had to function flawlessly or the rocket doesn't fly. On Mars, you have none of that. If you bring your returned fuel with you from Earth, You have to carry it all the way to Mars, land it on the surface, keep it stored for the duration of your stay, and then use it to launch. And remember the rocket equation. Every kilogram of fuel you bring for the return trip is a kilogram that had to be launched from Earth, transferred to Mars, and landed safely. The mass multiplier is staggering. That 21 ratio for landing. It gets worse when you include the fuel for the return trip, because now you're landing fuel that you need to launch. Let me try to sketch the numbers roughly. To get a crew off the surface of Mars and into low Mars orbit, you need a delta V of about 4.1 kilome. That includes gravity losses and a little margin. From low Mars orbit, you need to get on a transfer orbit back to Earth, which costs another 2.3 km/s. So just getting off Mars and heading home costs about 6 to 7 kilometers of delta V. With a good engine, say a specific impulse of 450 seconds, that means your rocket at launch from Mars needs to be roughly 80% fuel by mass. 80% fuel on a planet where there is no fuel. And it's actually worse than that, because the mass I just calculated doesn't include the heat shield you need for Earth reentry, or the life support for the months or long journey home, or the food and water, or the structural mass of the vehicle, or any margin for error. Include all of that, and the mass of fuel compared to everything else becomes obscene. Here's another way to see it. Remember, we got to the moon and back with a delta V budget of about 15 to 16 kilome. The total delta V for a round trip to Mars, including launch from Earth, transit to Mars, landing, launch from Mars, transit back, and Earth re-entry, is in the neighborhood of 18 to 22 kilometers s, depending on the trajectory and the mission architecture. That might not sound like much more than the moon mission, only a few extra kilome per second, but the rocket equation doesn't care about your intuition. A few extra kilometers per second when you're already at the edge of what's possible means an exponential increase in the fuel required. You're not adding fuel, you're multiplying it. Going from 15 to 20 kns of delta V can mean tripling or quadrupling the initial mass of the rocket. For the moon mission, the Saturn V weighed about 3,000 metric tons. A Mars mission with the same propulsion technology, bringing all the return fuel, might require a spacecraft assembled in orbit, weighing tens of thousands of metric tons. Nobody has ever built anything remotely close to that in space. But wait, I haven't even mentioned the cruelest constraint yet, orbital mechanics. The planets don't wait for you. Earth and Mars orbit the sun at different speeds at different distances. Earth goes around in 365 days. Mars takes about 687 days. They line up in a favorable position for transfer roughly every 26 months, 2 years, and 2 months. That is the synodic period. You can only launch efficiently when the planets are in the right positions. This means if you land on Mars and you want to come home, you cannot just leave whenever you feel like it. You have to wait for the next launch window. And depending on your mission architecture, that means sitting on Mars for anywhere from about 30 days to 500 days waiting for Earth and Mars to dance back into the right alignment. The most energy efficient mission profile is called a conjunction class mission. You fly to Mars in about 9 months. You stay on the surface for roughly 500 days, and then you fly home in another 9 months. The whole trip takes about 2.5 to 3 years. The long stay on Mars is not a choice. It's a consequence of orbital mechanics. If you try to shorten the stay, you pay an enormous delta V penalty because you're fighting the natural rhythm of the orbits. A short stay mission of 30 to 90 days on the surface requires a much more energetic return trajectory. Sometimes spending over a year in transit just to get home, and the total delta V goes through the roof, so your crew is on Mars for a year and a half no matter what. During that time, they are exposed to cosmic radiation with no protective magnetosphere, no thick atmosphere, just a thin veil of carbon dioxide. On Earth, we are shielded by a magnetic field that deflects most charged particles from the sun and from deep space. On Mars, that shield does not exist. The atmosphere provides a little protection, but remember it's 1% the density of Earth's. That means cosmic rays, high-energy particles traveling at nearly the speed of light are hitting the surface of Mars all the time, and they're hitting your crew. This isn't sunburn. These are particles that can shred DNA. They pass through the walls of your habitat, through the hull of your spacecraft, through your body. They break chemical bonds in your cells. The damage accumulates on the space station. In low Earth orbit, astronauts are still partially shielded by Earth's magnetosphere. Even so, they receive radiation doses many times higher than what we consider safe for workers in nuclear power plants. On Mars, the doses are worse. Over the course of a 3-year mission, the cumulative radiation exposure is estimated to be roughly 1 sphere, which significantly increases the lifetime risk of cancer. And there is no way to fully shield against galactic cosmic rays without meters of solid material around your habitat, which is mass you cannot afford to bring. They are living in a habitat that must be self-sufficient because the nearest resupply is about 9 months away by rocket, and you can't even send a resupply unless the launch window is open. If something breaks during the wrong part of the orbital cycle, there is nothing anyone on Earth can do about it for months, possibly over a year. If a crew member gets seriously ill or injured, there's no hospital. There's no helicopter evacuation. There's the crew's own medical training, whatever supplies they brought and hope. And psychologically, 4 to 6 people in a habitat the size of a couple of shipping containers, isolated from every other human being in the universe by millions of kilometers, and a communication delay measured in minutes for a year and a half with the knowledge that if something goes catastrophically wrong, no one is coming to help. Antarctic winter rover crews, submariners, space station astronauts, they've all taught us something about isolation. It degrades performance, it strains relationships, it affects judgment, and those missions last months, not years, and those people all know that rescue is at least theoretically possible. On Mars, it is not. Now let's come back to the fuel problem because I want you to really feel the weight of it. Suppose you are designing a Mars return vehicle. It needs to carry, let's say, 4 crew members with life support for the journey home, maybe 200 days, with a heat shield for Earth re-entry. With the structural mass of the vehicle, let's say the dry mass, everything except fuel is around 10 metric tons. That's actually very optimistic. It's probably more, but let's be generous to get a delta V of about 6.5 kilometers a second with a specific impulse of 450 seconds. The exhaust velocity is about 4.4 kilometers. The mass ratio you need is e to the power of 6.5, 4.4, which is e to the power of about 1.5, which is about 4.5. So your fully fueled vehicle needs to weigh about 45 metric tons for 10 metric tons of payload. That's 35 metric tons of fuel. 35 metric tons of rocket fuel on Mars, where there is no fuel, where the nearest gas station is 55 million kilometers away. And every